Hey guys, welcome. Yeah, so first, thank you, Lord Christ, for everything. I love you. You're amazing. Anything is possible with you. Lord Christ, please protect everyone out there. I know I'm in good hands. Yeah, very briefly, like as I've said in at least one other video in the past, like what's going on out there, obviously a punishment from Christ, because like this world is going a little crazy, but what is it? Like, yeah, if you walk with Christ, you don't have to fear anything. If he says it's your time to go, you're gonna go. Obviously, I am not a doctor. I'm not a trained physician, so I'm not gonna give advice on don't wear masks or wear masks. I will give you a mathematical perspective on wearing masks in a future video, a short video to come soon. But otherwise, you know, take caution, but fear only Christ, don't fear anything. Okay. Also, I couldn't find my other glove, so I had to wear this glove backwards. It's supposed to be on the other hand. Yeah, I know if I searched even harder for it, I could have found it and I could go out and buy a pair of gloves, but I don't want to. I want to find the other one. Yeah, so instead of searching harder for it, I thought it'd make like this kind of an interesting video if I just wear the one glove backwards and keep the other hand in my pocket so you can't see my hand. Okay, they're like regular human hands, I swear. No. Okay, and another random note is like, just in case that, like, you know, having the hand in one pocket is too casual for this video, I promise that the lesson will be very well delivered. But in case that's too casual, I thought I make up for it by wearing a tie. I have done that in previous videos, but yeah, I'm trying to set a trend. No, and final random note before we begin our lesson is, what is it? Yeah, so someone said that I have a few feminine traits, even though I'm a man's man. Like, I'm a man's man. But someone said that, so to make up for it, I bought this hoodie off of a female mannequin. How about that? Okay, let's get started. Enough random stuff. Okay. All right. So, multivariable domain and range. So, what is that for? That's for domain and range, right? And let's consider this function to start. Ooh, man, like doing and undoing these markers is hard if you don't have the use of the other hand. Okay, so let's consider this multivariable function. F of x comma y is equal to, by the way, like, I hope no one is like looking at me being like, oh, this guy's doing too much, because I have like one hand in my pocket. But if I want to do that, it's my right. So you're thinking that, first of all, I read your mind. Second of all, so what? Okay, let's consider f of xy is equal to x squared plus y squared. Remember, when we were in two dimensions, we would have f of x, right? And f of x is synonymous with y. That's because y is the vertical axis and x is the input variable which goes along the horizontal axis. This time our input variables are actually two. So we're selecting from the entire xy plane. So this is x, this is y, right? And this is z. So we're selecting from the entire xy plane an ordered pair x comma y, and the output, which is f of xy, that's z. So the analog to y is f of x is z is f of x comma y, right? And just like how in the single variable case y is the vertical axis, z, which is f of x comma y, is the vertical axis in the multivariable case, right? Okay, so what does this function look like? Well, I showed you how to graph multivariable functions in a previous video. It wasn't a dedicated video on graphing multivariable functions. It was like a part of another lesson. But yeah, what I said is like, what you could do is like, look at making x equal to 0, say here. So if you make x equal to 0 and the xy plane, right, when x is equal to 0, we have the y-axis. These are going to be xy planes, so this is y and this is x. So when x is equal to 0, we have simply the y-axis. That's in 2 dimensions. But remember, x is equal to 0 in 3 dimensions is a plane. X is equal to 0 in 2 dimensions is a line. X equals 0 is a line, namely the y-axis. That's in 2 dimensions. But x equals 0 in 3 dimensions is a plane. Specifically, it's the YZ plane, right? I'll highlight it. Okay, so x is equal to 0 is the YZ plane. This is what I'm saying. I gotta find that glove because this is nonsense. Okay. So x is equal to 0. When x is equal to 0, we have this plane, right? And so what we could do is we could take this plane, which is when x equals 0, and therefore the YZ plane, right? This plane is the YZ plane. We can take this and look at the outline of f of x comma y, which is x squared plus y squared, on this plane. On this plane, again, because x is equal to 0, this multivariable function is going to reduce to z is equal to y squared. Z is equal to y squared is akin to y is equal to x squared, only this time we're on the zy plane, right? This plane in red. So then we're going to have this, right? And then we're going to have this. It's going to be a parabola in the YZ plane, right? When x is equal to 0. And then similarly, when y is equal to 0, we would be on the XZ plane and we'll have another parabola. But again, this is not the lesson for drawing multivariable functions. So if we just very efficiently draw this function in 3 dimensions, it's a paraboloid. Right? And a paraboloid is just a 3-dimensional parabola. So it's going to look like this, right? Now I have to remember to not take my hand out my pocket, and I have to remember to erase backwards. I do have an eraser, and I know where it is, but it's fine, it's fine, it's fine. Okay. So let's stay on course, which is we're talking about level curves, right? So what do the level curves for this paraboloid look like now that we've graphed it? And you know, we don't need this outline of the YZ plane anymore. We're using it to get to our paraboloid, but now that we've got our paraboloid, let's get rid of this. All right, so what are these? Level curves. So level curves are when we set z to a number of fixed values, right? And so a student asked me, well, okay, so when we set z equal to some fixed values, what fixed values should I pick? Well, it depends, right? Like in general, like you should just pick z equals 0, 1, 2, 3, 4, and maybe 5, and that's enough level curves, right? So just, you know, a handful of z values are sufficient for the level curves, right? Okay. What's important is, like, if you pick z equals 0 and then you go to 1, then you don't go to 3, you account for every integer, right? Like, so 0, 1, go in sequence, go in order. And that is akin to, like, you know, if you're graphing some function and this is 1, right? Then don't say 2 is over here, because it gives the wrong perception on the graph. If this is 1 and 2 ends up here, you're saying this length is also 1 when this is 1. That's misleading as far as perception, right, of what's going on. So for the level curves, that perception you can capture by making sure that you're, you know, if you're choosing z equals 0, the next is z equals 1 and z equals 2, so you're going in sequence, in order. An equal increment is the better word. Okay, so if z equals 0, then the level curve for this function is going to be 0 is equal to x squared plus y squared. Okay, so this we can call the degenerate circle. So it's a circle in the xy plane with radius 0, right? So if I may draw this first level curve, and we're going to do it on this one, then that's going to be just that dot, right? So this level curve is just this dot. Yeah? Okay. So then, what's another level curve? Well, when we set z equal to 1, I have to go off camera so you don't see my hand. This is really silly. So we let z equal 1. Now it's a circle with radius 1, again centered at the origin. So what's that going to say? So that's going to say that we have, we have this. So if this is 1 again, and this is 1, right? This is 1. This is 1. So we have this. Now look, so clearly, sorry, so this is the level curve, right? Okay, so this is this level curve. Our first level curve was this. So by the way, you know, if it's not clear, what you're doing is you're taking this surface, which again is a paraboloid, and you're slicing it with planes and looking at the intersection of planes that are parallel to the xy plane and equally spaced. So you're looking at the meeting place, that is the intersection of these planes, with your curve. That's how you get to the level curves, right? Okay. All right, so next, notice, is letting z2 equal 2. Now, if you let z2 equal 2, right, then what's going to happen is you're going to have a circle, again, centered at the origin, but this time with radius root 2. So the student I was working with on this was like, well, root 2, I don't know what that is. Well, just be a nerd like me and know that root 2 is approximately 1.41. But, you know, what he's asking that for is instructive to say that we should change maybe the 2 to a 4, because now the radius is just a nice number. The radius is 2. But then that means that you skip from z equals 1 all the way to z equals 4. And this is what I was talking about as far as giving the wrong perception. So to make your level curves useful, just go up an equal amount along z. So what that means is next you should stick to z equals 2. So when z equals 2, then what we're going to get is a level curve that is again a circle centered at the origin, but with radius root 2, which is, as I said, 1.41. So if this is, remember, this was 2. If this is, sorry, this is 1 right there. So if this is 2, the 1.41 is like a little to the left of the midpoint between these two, right? So like say here. So then like doing the same. And see, this is why like the level curves are, it's very important to draw the level curves so that they are z's that are equally spaced. Because now, see, you see from the first level curve, they're usually called c's, right? So from c1, or let's call it that first one c0, since it's indexing when z was equal to 0. Then let's call this one c1, and this is c2. So notice the gap between c0 and c1 is bigger than the gap between c1 and c2, and this is why it's very important that we count z from 0 to 1 to 2 without skipping, because what this is telling us, the closeness of c1 and c2 when compared to c0 and c1, what that's telling us is how steeply graded our paraboloid is. And so like if I may draw these level curves on top of the paraboloid, this is c1 on the paraboloid, right? So and c2 would be like closer to it. Like, well, it's not closer to it as a vertical distance, but we can see like from like a bird's eye view from the top, which is what level curves are. They're like the planar slices the intersections of the parallel planes, and our surface looked at from the top, right? And that's what they are. So you see that like in this part, it's not as steep as this part. That's what the closeness of the level curves is telling us. It's telling us that in this part it's steeper, so in here, than it is in this part. That's why, again, it's important that you draw. Okay, so like, should I do more? Because I think at this point, like, it'd be abusive to do more. Like, obviously next is 3, and so that means that the radius of the circle is root 3. Again, be a nerd, because I know what that is. It's 1.73 approximately. So we actually don't even go to 2, right? Like, so 1.73 is like, so as we can clearly tell from the paraboloid, the steepness is like increasing, right? And so then that's what this is showing us, that the next level curve would be like even closer to C2 than C2 was to C1, right? Okay, all right. So I think you guys get the picture, so I'm not gonna do any more level curves. And accidentally, actually, I explained the meaning of the closeness or the distance between level curves sufficiently, but so usually I do like a mountain as the example, but that's kind of beating a dead horse here. But so you don't feel that you missed out, I'm going to talk about the mountain. So like, here's what I'm talking about. So like, how can we apply level curves? Suppose that you have a mountain that looks like this, right? And this is the base of the mountain. So this is like z equals 0. Obviously this mountain is three-dimensional, even though my visual doesn't lead you to believe that. Okay, so you see if I take a level curve here, right? Well, since it's a mountain, it's not going to be even. The level curve is going to look something like some jagged thing that's going to, this is going around the back of the mountain. It would look like that. And then, so if like this is, so if this is like C0, I'm saying like this is like some C1, let's say. Then C2, if we go in equal vertical distances, is going to be somewhere over here. All right, so C2 is going to look like this. So even though the vertical distance in this part and this part is the same, if we look from the top down, these level curves are going to look like this. So first I'm going to try to draw that level curve. So this is, I'm saying C2 and this is C1 down here, right? So C2 is right here. Okay, so if we draw them, they're going to look like this. So C2 is going to look like however I have it. And then C1 will look like this, where it is much wider, and this part showing that the mountain is not very steep in these parts as opposed to in that part. See how it is much closer in this part than it is in this part, the gap between C1 and C2. So this actually, thank you. This actually adds more to your knowledge, so I'm glad I decided to bring up the mountain. So this is C2 and C1. Yeah, okay, I think that's enough to say about level curves. Very quickly, I'll give you the example of level curves using my second function, and otherwise, I think enough said about level curves, don't you? Okay, all right, so here it goes. Okay, so this is really doing too much, maybe. Okay. All right, and the second XY plane is precisely for this. Now, I'm not going to know how to graph this by hand, but the level curves are going to reveal what the surface should look like, right? Like the level curves would reveal what the surface looks like, even if we hadn't graphed it in the beginning. We just looked at the level curves. You could get a sense of, you know, what it looks like, and that it must be a paraboloid, right? Okay, and so I'm saying that like the level curves not only tell us all the good things that I just spoke of, but they also like reveal what the shape has got to look like, what the surface has got to look like. Okay, so this second surface is defined by, I'm doing this off memory, so hopefully like my memory doesn't betray me, but it's defined by x comma y, so z, right, is equal to what? It's equal to, it was, I believe, the square root of x plus y plus 2, and then, silly enough, plus 2, but this time outside of the square root. And so it's good math grammar to write this 2 actually in front for now. I won't worry about it, so write 2 plus the square root, blah, blah, blah. Yeah? Okay, okay. So, what would the level curves for this guy look like? Oh, we do what we just did, which is we look at like what happens if z is equal to 0. If z is equal to 0, we're going to get 0 is equal to the square root quantity, right? And plus 2. So when we move the 2 to the left, we're going to get negative 2 in this part equals what? Negative 2 equals root, and then it's x plus y, and then plus 2, right? If we square both sides, and that's a 2 right there, my bad, guys. If we square both sides, we're going to get 4 is equal to x plus y plus 2. And then subtracting 2 from both sides, we're going to get 2 is equal to x plus y, which means y is equal to negative x plus 2. Got it. So this is when z is equal to 0, so we're going to call this C0. So this is the level curve C0. Got it. And then, similarly, like it doesn't really require a ton of imagination to know that the next one is going to be like when we make z equal to 1, we're going to get 1 on the left, and then we'll subtract 2, so we're going to get negative 1 on the left. We're going to square it, so we're going to get positive 1 is equal to what? Positive 1 is equal to, this is after squaring, so x plus y plus 2. And from this, it's easy to see that y has to equal negative x minus 1, right? And so this is C1, I'm saying. Okay, cool. And then, so C2 is going to equal, well, this is our final one, I promise, but we'll need C2 so that I can show you what the surface looks like from the level curves, right? Okay. All right, so C2 is going to be making z equal to 2. That's setting f of x comma y equal to 2. And when we do, upon subtracting that 2, we're just going to get 0 on the left. So we're going to get 0 squared equals, well, this is going to be free of the square root. So I wrote this too early maybe. So we're going to get, once we square both sides, we're going to get 0 is equal to x plus y plus 2. And solving for y here, we're going to get y is equal to negative x minus 2. Obviously, in each instance, instead of solving for y, we can solve for x, but that's really unnatural, so why would we do that? Let's just go with this. Okay, got it. So we see that C0 is right here, right? And C1 is right here, and C2 is right here. Okay, so if we plotted these level curves, they're all lines with slope -1, so it's easy enough. So C0 is like right here. I'm going to do them in red to stay consistent with what we did earlier. So right there, yeah? So I'm claiming that this is positive 2 right here, but otherwise I'm saying the slope of my line is -1, okay? And then the next level curve is going to be C1, and so let me label this C0. So this is C0. So C1 is, with intercept -1, so if this is -1, right, then this is going to be, it's going to look like that. Ugh, I didn't draw them parallel enough, not for my liking anyway. Okay, so we'll live with that. This is good enough. Okay. Yeah, okay. We'll pretend like it was a straight line. Sorry, guys. And then the next one is going to be like this, just at -2, right? Okay, that was much better. Still annoyed by this one being crooked, but sorry, guys. Like, dude, like it's okay, it's okay. So C1 and then C2 here, right? Okay. All right. So wait, this is really atypical, and that's why I'm doing it. In the sense that, like, level curves are usually circular, elliptical, or even on the mountain, even if they're like weird and crooked, they're basically a loop usually. So if the level curves are lines, what could the surface have looked like? This is what it could have looked like, right? So I'm not going to draw precisely this one, but I'm going to show you a surface that will convince you that it's possible to have level curves that are lines. So suppose that your surface is just, as my student who I was working with this on said, the surface is a weird plane. Like, so a plane that's like your bedroom sheets or whatever, like, you know, like making some weird, like, yeah, surface. So obviously on something like this, right, on a surface like this, all of the level curves are going to be lines. So that's how you could end up having level curves that are lines, yeah? Okay, cool. So I think I'm done as far as a lesson on level curves, and of course, saved perhaps the harder and more fun thing for a second, and that's domain and range. Let me not make you watch me as I erase, so I'm gonna pause the camera, erase, and then we'll get back. Okay, so I'm back and we're ready to discuss domain and range for multivariable functions. I actually took a substantial break after I finished our discussion on level curves because I realized that my camera needs charging. So like even for one little video like this, there are so many things that have to go right. The glove has got to fit, and camera's got to be charged, and so on. This is why life is exhausting, isn't it? Okay, all right, let's get on with it. You must learn and I must teach. So, all right, so let's begin with the first function we considered. F of x comma y is equal to, it was x squared plus y squared, right? So what's the domain and what's the range? So this part is over, so perhaps we erase this and make some space. So domain and range at their like core definitions don't change, right? Like, so domain and range, still same ideas. This is all possible inputs, right? Inputs, and the range is all possible outputs, right? So this is all possible outputs. And of course, since possible outputs, since outputs, okay, since you know, the possible outputs are completely determined by what's possible as an input, like the domain will have a great say in what's going to be the range. In fact, it has all the say in what's going to be the range, right? And so the first thing you want to do is figure out the domain of your multivariable function. And and otherwise, what else did I want to add? Oh yeah, obviously, like, you know, as always, figuring out what the range would be is very easy if you have the graph. In fact, this paraboloid is trivial. We saw what it would look like, right? So it's like a three-dimensional parabola that has its minimum value at the origin 0, 0, 0. So we can already tell that for this, all the possible outputs are going to be from 0 inclusive, because like the base of the paraboloid, right? This here was at the origin. It was at 0, 0, 0, x, y, and 0, all 0. So we see that the minimum value is 0, and of course the range this time is concerning z values, because f of x comma y is a z, right? So we would say that the range is z and 0 comma infinity. Obviously, you know, we don't put on arrows because this is not two-dimensional, but this surface will go on forever, like, right? It's an infinite surface, right? So you know, like technically they're kind of arrows, and so this part appropriate is infinity. And if you recall, like our inputs for this function, in fact any function of the type f of x comma y, all of the inputs come from the xy plane, and we can think about it, but it's pretty clear that in the xy plane all points are permissible in this mapping, right? So that means that the domain is all of xy plane, all xy plane. Okay, so as our second example, let's take f of x comma y is equal to, let's take square root of, say, and then what can we say? Let's say 4 minus x squared minus y squared, right? Like, so that, you know, you get a slightly different variety, different enough that like the thinking here will reveal something new that you don't already know, right? Okay, so like for this, right, to figure out the domain and range, let me first ask you for the single variable like situation. So if I had square root of 4 minus x, how would we figure out the domain or range? Well, we know that we're not allowed anything negative inside the square root. So what we do is, like for the domain, we'd say 4 minus x is greater or equal to 0, which means that 4 is greater or equal to x, and this statement is akin to x is less or equal to 4, right? So 4 or anything lower for x would work. We can think about it and just get to this conclusion. In other words, we don't need to write this methodical approach. Like we could be like, okay, so like obviously, as we already said, we're not allowed anything negative. So at minimum, we're allowed 0. What would make 0 is if x is 4. And then otherwise, if we plug in numbers less than 4, it's pretty obvious this quantity is going to be positive. And so then that's another way of getting to the fact that the domain of this function is x is less or equal to 4, right? So if we kind of have a similar take on this, first it'd be really helpful if we write f of x comma y as square root of 4 and then minus x squared plus y squared, like this, right? So it'd be better if we looked at this. Okay, so then now you see kind of by what we did over here, we'd be like, all right, so we're allowed x squared plus y squared is equal to 4. We're allowed this, because then we'd get 4 minus 4, which is 0. And we're also allowed for x squared plus y squared to be less than 4. And yeah, and continue in this matter. Now, if we look at this, right, like, so first of all, can x squared plus y squared be a negative number? And the answer is no, right? Because something squared at minimum is 0. So something squared plus something squared is at minimum 0. Something squared cannot be negative. So the sum of two squared items cannot be negative. So the smallest it could be is 0. And we see that x squared plus y squared equals 4, which is the largest value, which we got from considering the largest value that x squared plus y squared can take, which is 4, right? This here is a circle. So the domain for this function is going to be looking at the circle with radius 4. So let's say that this is 4, and so this is negative 4, and this is 4, and this is negative 4. So the circle would look like this, right? And as we said, x squared plus y squared cannot be negative, so the worst it could be is 0. X squared plus y squared equals 0 is a point, namely this point. So we see that the domain is the interior of the circle, and my bad, this is not 4, this is 2, right? The radius of the circle is 2. So we see that the domain is the interior of a circle with radius 2. So this is the domain, right? If we had like 1 over the quantity, notice then we have to exclude 4, because we cannot let the square root quantity be 0. And x squared plus y squared equaling 4 is what would make the square root quantity 0. So if we had 1 over this, then what we'd have to do is make the circle border dotted, because all we're leaving out is the actual circle. Anything else inside will work for this, right? Okay, cool. So I'll give you one. Oh yeah, we haven't said what the range is. So let's say the range, and I'll give you one more example. So for the range, as I said, the domain is very instructive, right? Like, so if we look at the domain, we see that the smallest value that we can pick for x and y is 0, 0. So one of the extremes in the domain is 0, 0. I'll say more on what I mean by extremes in the next example. So basically we're saying, like, for these two variables, like, what are the kind of equivalent to an interval, right? Like, so like, we know, like, if all the possible x inputs are like 2 to 4, then for certain functions, namely ones that are always increasing, to find the range, you just plug in 2 or you just plug in 4, right? So we're kind of trying to do that. And so 2 and 4 and what I just drew were the extremes. So we're trying to figure out what the extremes are here. One of the extremes is 0, 0. The other extreme is x squared plus y squared equals 4, right? And by 0, 0, I'm really saying x squared plus y squared equals 0, right? So the extremes are this and this. So if we plug in the extremes, when we plug in this extreme, we're going to get root 4 minus 0, which is root 4, which is 2. And then when we plug in this extreme, and again, we don't have 1 over in our function, we just have that, right? And when we plug in this extreme, we're going to get 0. So we see that the range for this particular function is going to be, we get the smallest value by plugging in x squared plus y squared equals 4, and that's root 0. And we get the biggest value by plugging in x squared plus y squared equals 0, and that's root 4 or 2. And it's including 0 and 2. So the range for this particular function would be 0 to 2. And again, these are z values. So z in there, right? Okay, cool. All right, so one more example should set us free, right? And so for that, let's do the function whose level curves are straight lines, right? And that's f of x comma y is equal to what? It's equal to, it was square root of x plus y, and then plus 2, was it? Right? Yeah, it's plus 2, but then the other plus 2 is outside, and I was saying that, like, it's probably better math grammar if we write it in front. Yes, still outside the square root, but in front is a little less confusing. That's, by the way, kind of digressing why we write I root 2 instead of root 2i, because, you know, it could be mistaken for like being inside the square root if we write it at the end. So I've said this in many other videos, but there's such a thing as math grammar. Okay, so domain arrange for this, right? Okay, so kind of like what we did earlier, right? Like, it's probably easier on the I if we write the inside is 2 plus x plus y, right? We're not allowed negative items inside the square root, right? And so what that means is that we need x plus y at worst to be negative 2. Because if x plus y, let's say, is negative 3, then in this part we're going to get the square root of a negative number. No good. In fact, x plus y is at worst equal to negative 2, right? Because then if it is, we're going to get the square root of 2 minus 2, which is 0, right? Okay, so what does at worst negative 2 mean? So we're saying that x plus y is greater or equal to negative 2. Is that what we're saying? Yeah, because if it's less than, as we said, it would make the inside of the square root. Okay, but then this, right, if we like manipulate it a little bit, says y is greater or equal to negative x minus 2. We know how to graph like linear inequalities, right? This is a linear inequality, and in the xy plane, it's going to look like what? This is the x, and this is the y, right? It's going to look like, well, negative x minus 2 is going to look like this, right? I have a different color marker. Like, will that help? I don't think it's like all this color coding stuff, man. Back in the days, people used to just learn on chalkboards. Now, everyone like gets all this giant excuse for their lack of like focus. I said, well, I know differentiating lessons I think is helpful, but in some places, you know, just do it. Okay, so here it is. So greater or equal to this line means like over here. But in case, you know, you weren't paying attention or you were confused by your lessons on graphing linear inequalities, if you were not sure which way to shade, this way or this way, because it's an inequality, we need to shade. But if you don't know which way to shade, just pick a random point on either side. I think it'd be really easy to pick 0, 0. And if you plug in 0, 0, you're going to get 0 is greater or equal to negative 0, which is 0 minus 2. Well, that's a true statement. So then that's telling you that we shaded in the correct direction. Okay, so this is our domain. Nothing else to say about it. So the domain in this problem is what? Y is greater or equal to negative x minus 2. Obviously, if somehow it is better for you to write this domain as x plus y is greater or equal to negative 2, okay, feel free. You can write it that way. Now, how do we do the range for this function? Well, let's see. So let's try and figure out the extremes, right? So the extremes we're saying is x plus y is at its smallest value that it could take is negative 2. So one of the extremes is x plus y is equal to negative 2. But what's the other extreme? The other extreme is that x plus y could be as large as we want, right? So the smallest it could be is negative 2. So we have to think a little bit about it. Like earlier, the circle was informative on the extremes. One of them was the center of the circle, the other was the border of the circle. Those were the extremes. Here, the extremes aren't so clear, other than we know that x plus y is at worst -2, so that means that we're on this line. Otherwise, it's pretty clear if you just think a little bit that x plus y could be as large as you want. There's no reason why you can't pick very large x and y's. So what that means is the other extreme is x plus y is like, I can't really say equal infinity, but I'm going to do it anyway. So we're saying x plus y can be as large as we want. Fine. So if that's the case, when x plus y is -2, here what we're going to get is 2 plus square root of 2 plus -2. So that's 2 plus square root of 0. So that's just 2. So all the possible outputs are, they start at 2, and obviously if x plus y is infinity, we're going to have the square root of infinity, right? Square root of infinity, whatever that means, right? Okay, which is a huge number, so let's say infinity, and plus 2, fine, is still infinity. So there we are, and that concludes this video. I hope you enjoyed it. Lots more to come. Keep watching. Stay safe, and pray to the Lord you're going to be fine. Take care.